lecture, we will be taking an example and how we can validate the concept we have discussed in the last lecture. So let us set the example. Consider an inverted pendulum with the following state space equation. Here we are given the E matrix of the system or system matrix 0, 0, 1, 0, 0, 0, 0, 1, 10.78, 0, 0, 0, minus 0.98, 0, 0, 0. This is E matrix, and control matrix B is given to us 0, 0, minus 1, 1. And C matrix is the output equation matrix. So here, first row is 1, 0, 0, 0, 1, 0, 0. And D matrix given to us 0, 0. So there is no fit through controller in the system. So here the state vector here, X is a state vector, theta X, theta dot X. And U is the control input, the force applied horizontally and theta is the angular position of the pendulum. And X, horizontal position of the part, position part, and theta dot X dot respective. The first question is design full state feedback regulator. And second question, design an observer using only one of the states. We can state. So let's solve this problem. We'll be using the concept what we have discussed in the last lecture. From the given system matrices, you can find the system equation in LTI form. This part already you have done multiple times. So now we'll start with the solution of the problem. Solution. So here, first let's design the state feedback control. So here we'll be using the concept Ackermann formula. Before that, we need to go through the basic steps for designing control. The first step is we need to find the P matrix. P matrix. P is basically we need to test the continuity of the system. So we can directly test CTRB A comma B, and then we'll find rank of P. If you enter, we'll get R equal to 4. So if R equal to 4, it is quite clear the system is controllable. Hence, the system is controllable. So we can design the state feedback control. And also let's check whether the system is stable or not. So for that, we can use the DAM command in MATLAB. So check system stability. For that, we can use this command omega n zeta. Omega n is the natural frequency, zeta is the damping ratio, and P matrix. And sorry, P is a vector which contains the poles of the system, whether the system is stable or not. So if you enter this command in MATLAB, we have the values omega n, zeta, and poles. So here we are getting omega n for the different state 0, 0, 3.2833, 3.2833. And zeta we are getting minus 1, minus 1, minus 1, and 1. And pole we are having 0, 0, 3.2833, and minus 3.2833. If you notice, in the pole location, one of the pole lies in the right hand side. So it is quite obvious system is not stable, right? So system since A is equal to 3.2833. So here is basically pole, one of the pole lies in the right hand side of S plane, hence system is not stable. Right. So we need to design the state feedback control, which will help us to shift the unstable pole to stable region. So for that, let us consider, select let us select a closed loop poles at S equal to -1 plus minus I, and S equal to -5 plus minus I pi. Okay, so we can write S1 to S3, 4. Yeah. 4 poles, right? Now we can use the command A. So we can use Ackermann. find the control gains. For that, we have already found the formula A into alpha minus A, P transpose P inverse, right? So here, if you notice, we have to find these parameters, alpha A, P, we have to find. So for that, we can first, so here, one thing, alpha are the coefficients. Alpha basically the coefficient of the characteristic equation, digit characteristic equation, and A is the, here A is the coefficient of the, our characteristics of the system matrix, right? So here, if you write alpha, actually nothing but alpha that you have done in the last lecture. Alpha is alpha n minus 1, alpha n minus 2, dot alpha 1, and alpha naught. And A here, A n minus 1, A n minus 2, dot A 1, A naught. So this is basically DGR closed loop characteristic polynomial. We are getting this. This is the coefficient of the S's, and this is basically blunt characteristic polynomial. Characteristic equation or polynomial, right? Since here n we found 4, we found 4 because system is fully controllable. And now let's find the blunt characteristic equation. Blunt's characteristic equation. So we can find this Si minus A equal to 0. And if you find it is difficult to solve the characteristic equation, you can use in MATLAB command. So here you can write A equal to poly so if you enter in the command, MATLAB command will get A equal to 1, 0, minus 10.78, 0, 0. Okay. And the characteristic equation from this roots, you can find this coefficient of the characteristic form s to the 4. So here SQ is missing because Z plus 0 into SQ minus 10.78 S square plus 0 into S plus 0 into S equal to 0. Or we can write s to the 4 minus 10.78 S square equal to 0. That's it. So here we can write, if you compare this with s to the power 4 plus A3 S cube plus A2 S square plus A1S plus A0 equal to 0. So if you compare both this equation, we'll get A3 will be 0 and it will be 0. A2 will be minus 10.78 and A1 is 0. This is equal to 0. So using these terms, we can form the P dash matrix. So here 1 minus A3 minus A2 minus A1 is 0, 1 minus A3 minus A2 and 0, 0, 1 minus A3 and 0, 0, 0, 1. Right. So you can follow how P dash K came here. In the last lecture, we have explained in detail. So now if you substitute the terms of A in this matrix, we are having 1, 0, 10.78 and 0, 0, 1, 0, 10.78, 0, 0, 1, 0, and 0, 0, 0, 1. Right. Now also we need to find the P dash inverse, because in the gain matrix we have this expression. We have found alpha. Sorry, we have found A. P dash we have found. Now we have to find P dash. This should be P dash. Similarly, we need to find alpha. For this, we have the desired correct roots are given to us. So V is given to us, desired roots, -1 plus I, -1 minus I, -5 plus I, -5 minus I. Right. Now, here also we can use alpha as a polynomial coefficient. So poly and alpha are found to be 1, 2, 72, 72, 1, 2, 0, and 100. Okay. So from this we can find the polynomial of alpha. So we can write s to the 4 plus alpha 3 is cube plus alpha 2 s square plus alpha 1 is plus alpha not equal to 0. And this is basically we can write SI minus ACL equal to, right? Or we can write from this we can write, if you substitute the terms, whatever terms we are getting here, these terms, if you substitute in this equation, we can write, we can find we have 4 plus 12 is cube plus 72 is a square plus 120 is plus 100, right? So now if you compare both this equation, we get alpha is a vector, which is 12, you write. So we can use only these terms for alpha vector 72, 120, 100. So this is alpha vector and A is given to us. So it is 0 minus 10.78, 0, 0, right? Now we can find the K equal to alpha say into P dash into P dash inverse. And if you write this command in MATLAB, we can get K equal to -9 to 0.98 minus 10.20 minus 24.24 minus 12.24. And this is the control matrix, gain matrix, which is going to find the state feedback control, right? This is, if you write this command, if you write this line in MATLAB, you can find this K matrix. Or even if you find difficulty, simply also, there is simplest way you can find also. K equal to, we can write K equal to A, C, K, E, R, A, B, and B. If you write this command in MATLAB and if you enter it, you'll get the same K, minus 92.98, minus 10.20, minus 24.24, minus 12.24. The same terms. So instead of going all these steps, you just simply write this command in MATLAB, A, B, and P. So A is the system matrix, B is the control matrix, and B is the your desired poles of the system to be used to design the control. So this is how we can design the state feedback control in MATLAB. So now we'll come to the second part of the question. B, we need to find the observer design, right? So here we need to consider, let us consider angular position of pendulum is available for measurements. Okay. Then if it is available for measurement, then we can find the y equal to cx. So only angular position, right? Only the angular position part. So angular position in the state vector, if you remember, in state vector angular position is actually, we are having theta here. So only we can in the C matrix, we can redefine the C matrix as 1, 0, 0, 0. That's it. So here we can write or y equal to theta. That's it. So we are assuming this. Now, based on this assumption, let's check whether the system is observable or not. So check observability. So we can use the command. So we need to find the N matrix, right? So N matrix you can find O, B, S, P, A, comma, C. And if you find R rank of N, we get R equal to 2. So it means if you consider our C matrix, if you consider C matrix in this structure, system is not observable. So plant is not observable. This is, you have to play in this design the observer. You have to think how can choose the C matrix that the system is observable. So this is a very important part for designing observer. So now we have to again redefine the C matrix. So in the second, let's have a second try. Let's check, let's assume output output measurement to be cards position only. So in this case, we can say y of t equal to only x of t. So the output equation we can define y equal to cx, where c you can since let's check where is x coming in the state vector. So x is in the state vector actually second term, right? Here x is the second term. So second term that x vector. So we can write the C matrix as 0, 1, 0, 0, and x. So here we get accepting card position, right? Now again, let's check the rank of the observability test matrix. So let's find in, if you write OBSV E comma C, and if you find R equal to rank of N, and if you enter it in the command window, we can get R equal to 4. So now the system is observable. It's full rank. System is observable. So now then we can proceed the same way what I have done before. Now design the observer. For that, first we need to find observer gain matrix, right? So for that we need, let's consider the observer poles at is equal to, so let's consider the observer desired poles. Desired poles at is equal to -10 plus -10i, and is equal to -20 plus -20i. So if you remember, we considered in the previous lecture that the observable poles should be more negative compared to the regulator poles, right? So if you notice, our regulator poles much lower than these values as magnitude. So now we can form the V matrix here, desired pole or V vector, which is the desired pole of the observer 10 minus 10i minus 10 plus 10i minus 20 minus 20i minus 20 plus 20i. Okay. And if you write P polynomial P V, if you write, we will get the entire P we are getting the vector 160 180 24 1800 2400 and 160 000. And from this we can write the desired characteristic equation s to the power 4 plus 60s cube plus 1800 s square plus 2400 s plus 1600 equal to 0. So here it is nothing but beta 3, beta 2, beta 1, and beta naught. So we can form the beta matrix for observer 60, 1800, 2400, 160, 000. Right. And already we had the A matrix found 0, minus 10.78, 0, 0. So now we can find L, the observer gain matrix. We can find L equal to, we know the equation already you have found. Sorry, this A into A dash into N minus 1. Here that's been transposed. So now we get L equal to minus 25149 16 minus 183 and 1810. Okay. So this is the observer gain matrix. This is numerically we can do. So now, using this gain matrix, we can find the observer's augmented system or system matrix. We can write, let's write system matrix. So this is A naught equal to A minus LC, right? And this is basically, if you remember, we had E dot naught equal to A naught, E dot, right? So this is the A naught. The eigenvalues of A naught should be negative so that E dot goes to 0 as t tends to infinity. This is the main motivation to design the observer. The error between the actual state and estimated state should be 0. So now if you find the eigenvalues of A naught, so let's define E equal to this. If you enter it, we get the eigenvalues minus 20 plus minus 20i and minus 10 plus minus 10. So if you notice these eigenvalues of this A naught matrix, all are lies in the left-hand plan, or lies in the left-hand plan. One may be here, minus 10, that's maybe here, it's 20, so one is here, one is here. So these are the eigenvalues location, and all eigenvalues are in the left-hand side. So system is stable. So E naught is going to 0. So system is, all states are available in the measurement. Sorry, all states are estimated to design the state feedback control. So we can easily find the control algorithm for regulator. Now we have prepared the code for this system. So these are the codes we can use. So for this particular example, so here is the controller design part, and this is the part for observer design. So you can use this out for your reference. You can validate. Um, you can validate this, whatever the mathematical things you have done in this whole lecture. Also, the same way you can proceed for the observer and controller design for other system, for aircraft or any other aerospace systems. Just you have to change the matrices. That's it. So let's stop it here. We'll continue from the next lecture. Thank you.